if you remember me talking about mutability, immutable things. Raise your hand if you remember what that means. A couple people. Here, I'm just gonna. So, when you have something that's mutable, you can change it. You can go in it and alter some information about it. When you have something that's immutable, you can't. So we saw, like with strings, they were immutable, right? Once you create a string, you can't go into that string and change anything about the string. You can make a new string. You can make a new string based on the old string, but you can't actually change anything about the original string. Lists, on the other hand, were mutable. You can go in and change and alter and update whatever's at its index. And you'll see that all the objects we write are mutable. Case in point right here. I'm saying my sphere x, when it was created, x was 0. But then I went and I changed its value. Meaning that objects, as we are doing them here, are mutable. We can go and change them. But you may also remember me talking about how sometimes, your knee-jerk reaction might be, well, I prefer mutable. I like the ability to go in and change things. And you might feel that way at that stage. But as you go and become a little bit more familiar with programming, when you have mutable things, it ends up being a recipe for disaster. When you've got simple problems and programs, fine, but as you start growing more and more complexity, it ends up, if you make all your stuff immutable, you hedge against potential problems. In Python, there are a couple of ways we can go about making things mutable versus immutable, like these objects. Maybe we can change it so they're immutable. But you can't actually really stop it. In some other programming languages, there's ways that you can enforce that, okay, here's an object and it's immutable. You can't change anything about it. Where with Python, we kind of have the flexibility to do whatever we want, which is great, but sometimes you really shouldn't be doing those things. So just as a warning, I don't really have a specific example right now, but just as a warning. Assignment 2 has a good example of immutable data. The cities themselves, which were represented as a list, has a name, had an infection status, true, false, and a list of neighbors. And there's nothing saying that you can't go in and change the data. But if you go and you look at your infect or cure functions, if you did it right, you actually make a copy of the city with the copy being the infection status set to true or false, depending on which function you were using. So although you could go in and change it, if you were doing it right, you actually have these functions that make a copy of the data and alter those copies and kind of leave the original ones alone. And the value here is, you might remember also how we had that when the simulation step, there was the before state and after state. The before state is like, okay, well, this is the state of the world before the simulation step occurred. And then the after state is what the state of the world looks like after the simulation step occurred. And the reason we separate it like that is, well, really, that simulation step where we have to iterate over all the cities, really we want them to be happening like all at the same time, but the computer can't do it, because the last thing you would want is to go and have city 1 infect city 2, and then city 2 can start start spreading the disease, even though, city 2 really wasn't infected at the start of that day. They only got infected during that day, so maybe they shouldn't have been able to. But by making use of this infect and cure, and kind of making it so your data is immutable, you can't accidentally go and alter the original one. You could in Python, you totally could, but if you're using the functions properly, it protects you against it by pretending it's mutable. Just as an FYI. All right, back to what we were doing. Sphere. We've got our constructor, our initializer. It's got 4 attributes, x, y, z, and a radius. X, y, z is the x, y, z coordinates of the sphere in some 3-dimensional space, and spheres need to know the radius. Great. Next, let's start adding the functionality. Let's start adding the methods. Well, we'll start with those simple geometric ones, or geometry-based ones, pardon me, like diameter, surface area, and volume. That's like, well, diameter, surface area is like circumference, and volume would be like area, but 3D, right? But we're also going to want a couple other functions here. We want to measure the distance between centers of spheres. So I want a function that can tell me if you have two spheres, or function, I want functionality, where if I have two spheres, I want to know the distance between their origins. And maybe I also want to know the distance between the edges of the spheres. So not only like, okay, I know the distance between the center points of two spheres, but maybe I also want to know, well, how close are two spheres there? And you can imagine maybe if you're rendering 3D graphics or something, you want to keep track of this because maybe you can check for collision, right? Are these two things overlapping or not? I want to know if these objects are colliding. So this type of functionality is very, common, I guess. So we also want to know if spheres overlap one another. We should also have a way to know if two spheres are equal, if they're equivalent. And what we're going to want is, now you saw before, if I go here, let's run this. If I print out the sphere, it says sphere object at that memory address. Great. But, that's not overly great because it doesn't really tell me a lot about the sphere. It just tells me that, well, this is a sphere and it's at that memory address. So we can actually go and tell Python, well, when you print out the sphere, maybe print it out like this. But that'll be what we hit near the end of this topic. We like better string versions of our objects that give us more detail about what's going on. Just think of the list. When you print out a list, it doesn't say list at memory address blah, 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 blah. It prints out that nice format like square bracket, the data, commas, square bracket, right? Someone wrote the code to be like, okay, Python, when you print out a list, this is what you should do. So we could do the same thing for spheres. Maybe you really do want something like that. Or maybe you want to be like, well, this is a sphere at index, or at x, y, z with a radius of this. It's something a little bit more descriptive. So here are the three initial methods here that we're going to want to add. Diameter, surface area, and volume. I'm just going to go back here. Put them in, make sure everything is at the right indentation level. I run this. Now I can ask the sphere, hey, what's your diameter? And it's going to be like, all right, well, what's my radius? And just return to that. What's your surface area? Well, I'll just do the calculation. What's the volume? Well, I'll just do the calculation and return the value. But again, notice these three methods here, the functions, don't take any parameters except for the self one, which we're aware of. But then I didn't give it a radius. No, because this method doesn't need a parameter for radius because it can just know, it just knows that, well, this sphere object has a radius. So you don't need to give me a radius. When I tell a sphere, like, hey, give me your radius, it already knows its radius, so I don't need to give it that information. It could just tell you. So I hit run, I'm going to hit run. Well, here, actually, let's do like diameter, and then sure enough, it's 20. Great. So this is very, very, very similar to what we saw with the circle, right? The circle we just defined. We started defining the class. We had the constructor, initializer, and we had a couple of methods. The methods were like your diameter, circumference, and area. So this is very similar. But now we're going to add that extra awesome functionality. Okay, blah, blah, blah. Let's start with distance between centers. Well, if you're a little worried about, oh boy, like what on earth, how on earth would I do that? Well, I'm willing to bet you definitely know how to do that. Here, we'll just do it like this to help break it up. Well, what it is this is just a Euclidean distance formula. You might be more familiar with it in 2 dimensions where you take the, pardon me, where you take the difference of the x coordinates and square it, and add it to the difference of the y coordinates and square it. If you have more dimensions than just 2, you just keep doing that for every other dimension. You the third dimension, so the z coordinates, take the difference, square it. After you added them all together, you take the square root. That's just Euclidean distance, right? And if you've ever been scratching your head about Euclidean distance and wondering why is it like the exact same thing as like a triangle finding the hypotenuse, because that's what it's doing, right? You can envision 2 points in Euclidean on a coordinate system, and you want to know the distance between these 2 points. Well, you just find out the difference between the x's and the distance between the y's, and then it's the hypotenuse. It's the same thing with Euclidean distance. It's the same. It's the same thing. Just FYI. You just may not have thought of it like that before. So that's what's happened. But notice, this method takes a parameter. It takes the parameter other. And here's why. This might be weird to you, but let's go back to the topic and say, consider how I would call this. This would be how I would call it. I have sphere A and sphere B. If I said sphere A, distance between centers, sphere B, that's going to tell me the distance between sphere A and sphere B. What would happen if I actually changed the order? What would happen if I said sphere B dot distance between centers, sphere A?
You get the same output.
It would be exactly the same. It would be the same, right? So order doesn't matter now. So the function is, okay, sphere A, tell me how far away you are from sphere B. The alternative, if we did sphere B dot distance, it would be sphere B, how far away are you from sphere A? I will also say, really quickly, notice that the type hint is actually within quotes. That's because in the current version of Python, although I think maybe I saw something about this getting updated soon, but I could be wrong. Whenever you have a thing where like, okay, well the problem is, Python doesn't know what a sphere is because we're defining a sphere. But if you do, like, so if we were to do this, it's going to be like, I don't know, like, what is a sphere? Sphere is not defined. When you put it in quotes, it's like telling Python, shut up, it's there, trust me. When you hit run, you're going to know it's all fine, right? So just, that's why it's in quotes, because, well, what's a sphere? Well, the trouble is we're defining it right here, so you put it in quotes. But the parameter I gave it is other. Now this right here might really help you conceptualize the importance of self. So, I'm saying self x, what's the difference with the others x? So in this case, if we go back to this example of sphere A dot distance between sphere B, which sphere is self?
Sphere A.
Sphere A. And then other would be sphere B. If I switched them, well, we would just switch those as well. So I'm saying, okay, sphere A, the self, how far are you from the other sphere in x coordinate, y coordinate, z coordinate? So this really, I think, to me, makes it a lot clearer where it's like, okay, the difference between the x's. Well, whose x's? My x and your x, the one I'm trying to compare to. So this might help a little bit wrapping your head around self and how it's valuable. Because if I didn't have like the reference variables and I was doing something like this, what the hell does this mean? Right? That doesn't make, well, so, like, okay, no, it's self's x minus the other's x squared. The same thing for y, same thing for z. So there, great, distance between centers. We've got a working function. And let's do this here. I'm just going to copy this code. Great. If I have a sphere at 1, 1, 1 and a sphere at 2, 2, 2, the distance between those, I guess, is the distance between the centers, which is 1, 1, 1, 2, 2, 2, is 1.732050807, whatever. So there, great. I now have a method to tell me the difference between the centers of two spheres. Cool. Notice how now we have interacting objects. I have an object take reference to another object of the same type, sure. But I have interacting objects. The objects are now interacting with one another in a very nice, clearly defined way. Just compare the differences in the x's. But we have interacting objects. And we can see how we are using objects interacting with one another to do stuff, which is cool. Yeah, there we go. And here's the note on well, you'll notice that sphere, well, that's just to make Python shut up. So now, let's write distance between edges. So now what I want is not the distance between the centers of two spheres. I want to measure the distance between the surfaces. Now this is kind of weird though, right? Because the difference between the surfaces, it's obviously I want to measure the distance between the surface point on sphere A that's closest to the surface point on sphere B. Right? If I had, I'm just going to draw two circles. This is probably hard to see, this is not a great marker, but bear with me. Two circles. If I want to know the distance between the surfaces, the edges of these circles, well, I want to know the distance between the smallest gap between them. That's the trick here. I'm not going to measure the distance from this point to this point. That's just ridiculous. Fortunately, this is actually rather simple to do. All I have to do is measure the distance between the centers, right? If I know the distance between the centers, if I know the distance between centers is x units, so all of this is x, how do I calculate that value? Everyone's putting up your hand because it should be pretty obvious. Well, it's just x minus r1 and r2, right? And we're lucky because that's guaranteed the distance between 2 points. Well, that's going to give you the shortest path. And we know the radius is of both spheres, so we can just get rid of that point. Great. So how are we going to do this? Well, I could go and redo this calculation here. Calculate the distance between the 2 points and then minus my radius and other radius. I could do that. But remember, you don't really want to duplicate functionality because that's a recipe for disaster, because if you update it one place but you forget the other place, it's a mess. So what we do instead is, well, we can just call the method distance between centers, get the value back, and then take away my radius and your radius to know, well, how much is actually left. So I'm just going to call the function distance between centers within my distance between edges method. But if I want to, just like how if I want to access an attribute, a variable that belongs to an instance of that class, I say self.x. If I want to access that object's methods, well, I still have to use self. So I say self.distance between centers to the other, then minus my radius, the self's radius, and the other radius. So now we've got this method calling another method. But the key observation is, in order to access that method, I need to specify, well, that method belongs to the self. It's that sphere's method, distance between edges. Or method, distance between centers, pardon me. Any questions about that? All right, great. So now, let me quiz you. How can I know, let's assume for a second I give you the function or the method distance between edges. If I want to know if two spheres are overlapping, how can I do that now?
You just see if the value, like if it's positive or negative, the value between the edges.
Exactly. If the distance between the edges is positive, well then I'm in this type of scenario. If, however, we have a situation where, let's say the circle looks like this. I know it's not a circle. If it looks something like this, and I said, well, x minus r1 and r2, I'm actually going to have this like negative distance here. Meaning, well, if the distance between the edges is a negative number, that means I know they have collided. They overlap, that's for sure. There are other ways we can go about doing it, but to me that's the easiest way. And if we go look, overlaps, there. Let's go look at it. No. Just return if the distance between edges is less than or equal to 0. So I guess based on my definition here, if the distance between the edges happen to be 0, then we will say, well, they're colliding. They're touching. They are, in fact, touching. Maybe you think like, no, that doesn't make any sense. It really should be this because it has to be less than if they're touching. They're not really overlapping. Fine, great, whatever. This is just how I wrote it. So now I can check if two spheres overlap. Let's see if sphere A overlaps sphere B. And, well, what did I do wrong? Did I not run this? And it also need to call the function correctly. True. So sphere A and sphere B do in fact overlap, but it's kind of cool because overlaps makes use of this method distance between edges, which makes use of the method distance between centers. So you kind of have like this cascading method calls, which is neat. But this isn't anything new. We've had functions calling functions before, right? We know that. It's just the same idea, but now it's methods, and because they're methods, we need self. I'm going to guarantee you, you are going to make method calls and you're going to forget self. I do that all the time. I always forget to do that. And I spend way too long going, why? It's right there. I just defined it and it's saying it's not there. And it takes me way too long to always remember, oh, I forgot self. Shoot. Other programming languages kind of do. So I suppose we're now at the part of the semester where we can take a moment to talk about good things and bad things about Python as a programming language. Python is a great programming language for learning the basics, in my opinion, when talking in the context of a learning programming language. Now, I use Python a lot in my everyday research and whatnot, just because I like to use it as well. It's really good at that. But when we're talking about a programming language to use for the learning purposes, Python is great for this type of class. It's fantastic. But the problem with Python is Python's really happy to give you as much freedom as you want. It's really happy to be like, you want to make all your stuff mutable? Great. You want to have a constant that you can actually change its value later? Whatever, I don't care. It's up to you. Python's very nice. It gives you a lot of freedom. It gives you a lot of rope to work with. But of course, as we all know, the more rope you have, the more likely you are to trip over that rope. It starts to create issues. Some other programming languages, like if we take a moment and talk about a language like C or C++, those are older languages. And they have what they are good at, they are good at. Now, in those languages, they kind of take the philosophy as like, you know what you want to do, anything goes. But the difference here is when Python says you can do what you want to do and you mess up, Python's a little nicer about, when you shoot yourself in the foot. It's like shooting yourself in the foot with a Nerf gun in Python. In C, C++, when you mess up and you think about all the extra overhead, it's like you shot yourself in the foot with like a bazooka or something. Good luck. But once we get past this introductory stuff, Python's freedom, the amount of rope it gives you to trip yourself up on, becomes a bit of a problem. Some other languages give you much less freedom. That's a bad way to describe this really, but I'm just going to use this as my example. It gives you much less freedom. It's a lot more constrained. There's a lot more rules you are to follow. A lot of the rules that you are to follow, you don't have to follow, but you should follow. And when you follow those rules, those languages enforce certain things on your code. Having those constraints make programming in complex programs way easier. Because you don't even need to hit run on your code before those languages be like, no, you said this function was going to get 2 integers, and you passed it 2 strings. It won't even let you run it. The programming language won't even compile. The program won't compile. The program, like Java, for example, will be like, I can't run that, you blew it. So it's telling you where the problem is before you even run the program. A lot of people think, oh, all this extra overhead and constraints that Java puts on me. I'm just using Java as an example because we're doing Java next semester. You start to think, oh, that's all this extra work. I don't like it. I really miss Python. Trust me, you don't. Because Python is how you're going to mess up. It's great for this level of stuff. Then after you've spent some time learning more about programming, by all means, go back to Python and do whatever the hell you want. It's just Python's philosophy of like, do whatever you want, I trust you. I really hate to say it, maybe you shouldn't trust a first year, second semester student that much, because they are going to blow it. Everyone does, but that extra rope becomes a little bit hairy. So when we move to another programming language next semester, if you're in 162, don't consider it a problem. Consider it a like, oh, thank God. Because it's going to make things so much easier going forward, just as an FYI. All right, distance between edges, great, overlaps. Now we're going to talk about magic methods. Sometimes they call them dunder methods, because these are the methods that pop up with the double underscores. Actually, I should hit pause. Does anyone have any questions about my little rant about the programming language? Just curious if anyone has any. Yes?
At a higher level, is there ever going to be a point to come back to Python, or is it just like, at that point, just learn new languages?
It'll depend on the prof of a course. So a lot of times, once you get past second year, and then you take a course, no one really cares what programming language you use. It's just do this. I mean, unless you're taking a programming course on like, this is the Java course or something. Okay, yeah, it's going to be in Java. But once you get past a certain point, they'll like, whatever, do what you want. I mean, they'll have some constraints. They'll probably want it to be like an open language. So like they'll say no to certain languages like MATLAB, because MATLAB you need to pay for a license to run, and programmers don't like MATLAB a lot. So, you know, MATLAB's weird. They index at 1. What? Who starts counting at 1? What? Makes no sense to me. Especially after all I've taught you about why we start counting at 0. Oh, it's a mic. Interesting question. I mean, students will, by the time you get to 3rd and 4th year, students will say like, I'm going to do assignment 2 in this class in Go, because I just want to learn Go. Great, what a great way to just challenge yourself to learn a new programming language. Because by that point in time, you know how to write the algorithms for what you want to do. It's just, well, what's the syntax for that specific programming language? Interesting question. All right, magic methods, or dunder methods. These are methods that we invoke, not directly. You can, but you don't. So, for example, the init. Did we ever explicitly call circle underscore underscore init underscore underscore? No. It got called indirectly when we said my circle equals name of the class. When you type in the name of the class and hit enter, it knows to go run the init method. Specifically, what I'm referring to is right here, sphere. When I call the name of the class sphere, this is like, okay, I'm creating a sphere. And Python goes, okay, it's the name of the class, but I'm just going to go call the constructor. I'm going to call init. You don't have to call it directly, I'll do it. But this is where you define it. So when you call sphere, it actually runs this method. There are a couple other methods like this. There's actually a lot like that, but we're going to cover 2 very important ones. Equals and representation. So what does it mean for two spheres to be equal? Right? How do I know when two spheres are equal? We get to define it right now. I would say for our purposes, let's consider spheres equal if their x, y, z coordinates are equal and their radius are equal. Meaning they are the same size and occupy the same space, right? So this is a relatively straightforward equals. Compare all the attributes between two spheres. If they're all the same, return true. Otherwise, return false, because then they're not equal. Because by default, whether you write an equals method, whether you show up and define an equals method, thereby defining what it means for two spheres to be equal, Python gives you one for free. I can already check if two spheres are equal in Python. I can just ask. I can say print I can run this and it's false because, yeah, those two spheres are different. But if I make them the same, it's still going to say false. What I would have to do, the default equals that Python gives you is, I'm going to test you right now. You can figure out what it is based on what I'm going to do. There. So what is the default equality there? Well, true is these two, in this particular case, this is the important bit. What are you thinking?
It's checking like if sphere B is sphere A, not if the parameters are the same.
Exactly. What it's doing is it's literally telling you if they are the exact same object. Because sphere A and sphere B are two aliases for the same object. In this code right here, there is only one sphere created. And I have two references to that sphere, so the default equality is, are they literally the same object? Are they literally the same one object in rank? And if I were to print these out, if I were to print sphere A and sphere B, we can see, well, yeah, they actually are in the same memory address. This is the exact same. They're there. Cool. But that's not always overly helpful, so we define our own. As soon as we define our own equality, it throws Python's default one away. We override the default one. That's the word we would use. We override it, meaning, I know you gave it to me, Python, but get lost. Here's what it really means to be equivalent. And here's how we go about writing our equals method. I do this. I'm just going to copy all this code and then put it into Colab, because I think it's a little easier to look at there. By the way, those of you at the back, is this easy to see?
Yeah.
So there's that. I'm just going to go like this. No, how do I have to do this? No. Well, this is going to be like the distance one, where you had self and other. But I'm checking, is my x the same as the other's x? And is my y the same as the other y? And are the z's the same? And are the radius the same? That's what it means to be equivalent for our definition. If you don't like this, if you're like, no, you know what, I think for what I need, equality for two spheres should only be if they have the same radius. I don't care where they are. We will consider these spheres equal if they're the same size. If that's what you need, great, because remember, we are defining what it means for these to be equal. In my example, I'm going to check if all attributes are the same. Maybe for your needs, it doesn't matter where they are, it just matters that they have the same size, so you would write your equals that way. There's no one right way to write equals. The equals is, well, what do you need for your use? What do you need? For your use, what does it mean for two things to be equal? So there's not one right way. It's just, I just did it this way, check all attributes, because why not? So, like I said before, these methods, these magic, these dunder methods, you don't call them directly. You can, but don't, because everyone will make fun of you. What I mean is, do not go do this. Here, I better rerun this. Okay. Sphere A dot sphere B. Oh. Okay, that's not what I wanted. Now I'm going to make sphere B back to what it was before, not actually be there. So these spheres are different because the z's are different. So when I call run, false. If I make these the same, true. Don't do it this way though. I invoked the equals method by calling the equals method directly. Don't do that. The way we would like to do this is like this. Like how you've done it every other time. True. They're not the same object in RAM, yet now when I use equals equals for comparison, it's using the underscore underscore EQ underscore underscore method. So this, when I make use of equals equals, it goes and calls this method for me. Just like init, I never directly called init. I just called the class name, and that called init. Now when I do equals equals, it calls the EQ method. Yes?
Where's the other value coming from?
The other. So in this case, so when we go back to this, it's a little bit more obvious, right? Because here, sphere A is self, and sphere B is other, right? It's quite clear because, well, that's the one I passed as a parameter. Not sure what just happened there. Of course, I lost all that code. Shoot. Let me go back, see if I have an example. Here we go. Here, I'm actually not 100% sure on the order. I'm just going to assume that when you use it like this is like the instance we are calling it on. This would be the self, and this would be the other. So it just goes and goes like, well, okay, really this means like really it means that, but we don't like to write that. That's ugly. What we like is, well, to check a quality just like how we check the quality on everything we've seen so far by just making use of the equals equals method. If you were to go check if two strings are equal in Python, you say my string, or string A equals string B, it goes to the string classes underscore underscore EQ underscore underscore method. It's using that. You just don't explicitly call it. Every equals equals you've ever done is going to be making use of this equality method, but you just don't call it directly. So this is how we define equality, but we don't like to call the method this way. We like to call the method indirectly by just using the equals equals operator. Does that answer your question?
Yeah.
Cool. Any questions? Any more questions about that though? If I see anyone do this, I'm going to call your parents to make fun of you to them. Don't do this. This is bad. Don't do this. And you'll lose marks. And then you're going to be like, well, it's not wrong. And we're going to go, but it is. It is. Okay? In the same way that you had bad variable names, and in the same way you had terrible comments, this is wrong. Now, there is a note I want to make. Imagine for a second, now I actually don't have the circle class created in this Colab notebook, but pretend I did. if I were to call this, I'm checking equality. Well, I've defined equality for spheres. But if I call this like this and say, well, some sphere equals some circle, we're going to have an issue. Because the circle doesn't have an x, y, z coordinate to compare to. We've got a problem. This is going to crash your program. But the fortunate thing is, well, you know, if we ever give a sphere, if we ever try to check equality on a sphere, and the thing that I get, that other, isn't a sphere, can I conclude if those things are equal or not already? Of course, I can conclude, well, they're not equal because they're not even of the same type. So an easy way to fix this is to just do, all right, if it's an instance of a sphere, so there's this special function that exists where you can give it a reference variable and the type. If it's an instance of a sphere, then go ahead and do the check. If it's not, just immediately return false, because I don't care. It's a sphere and a circle aren't equal because they're not even the same type. So this is the right way to do equals, is to also have a check to be like, well, am I even comparing things of the same type? So this is a much better equals, because it's safer. It won't randomly crash. Oh. Great. And now if I do, well, it won't work because I don't have a circle, it's fine. But if I did and I hit run, it would say false. Because they're not even, the sum circle, which would be the other, isn't even a sphere. Now, this is just a note saying, like, you know, I didn't actually have an equals for the circle class. Should I? Yeah, maybe you should. Maybe you don't need one, maybe you do. If I wanted an equals method for the circle class that we wrote last time, that's what I would do. Just check if the radiuses are the same. Great. Now last is repr. Repr is, well, what is a nice string representation of this class? Like I said, consider the list example. If I were to run this, A, B, C, and then if some can do whatever, print out X, I would see like bracket A, B, C, maybe X, close bracket. It doesn't say, oh, list at memory address OX7F5217F, whatever, right? It doesn't say that. It gives me more useful information. Now, these reprs are often very handy to the programmer, right? Because you know how, like, when you're debugging your code, maybe this is an example of you doing some debugging, and you're like, you know, the condition should be met, but maybe it's not. So I'm just going to quickly print out some list, and if I don't see X on the end, I know I have an issue. So it's often very helpful for these reprs, to have these reprs for the programmers, to see what is their data that they have. Because seeing sphere at OXB2714F002 is useless. It's not very helpful. Maybe it is for what you need, but chances are it's not. So what we could do, well, so again, here's an example of me calling it on sphere. I might see something like this. Not all that helpful. So what I can do is I can define a repr. And this is going to say just sphere, and then tell me what the x, y, z, and radius is. So if I hit run, I do this, and now, when I call print on some sphere, it tells me, oh, it's a sphere, x, whatever. And that's just the format I use because it looks like how you would call the constructor. We can make it way different. We can add, blah, blah, blah. Great. And now when I run it, it just also includes a bunch of nonsense, because it just does what I tell it. But there we go. And again, you don't directly call repr. You can, but don't. We make fun of you. You do that by saying, like, we'll just print something. Or you can tell me what the string version of something is. Or you can also call repr. But again, you're not saying some object dot underscore underscore repr underscore underscore. There you go. This, I don't think I've ever actually seen anyone do. This is handy if you're doing things like string building. But for the most part, the way you're going to use this is like this. Just print it out, and it does it. I'm going to get rid of this nonsense because that's not overly helpful. There. So there, great. But again, I don't call this magic method directly. I indirectly invoke it by just saying, well, print it out. And Python's smart enough to go like, well, they're going to want a nice string representation of this thing they just printed out, so I'm going to call repr that they defined. But based on what we know, it might be obvious to you that, well, Python gave us a free repr. It gave you a repr for free. If you don't write one, it gives you one, just like how it gave you an equality for free. But equality wasn't all that helpful. The repr you get for free is name of the class, memory address. So we're going to override that and be like, no, shut up, here's the real one. All right, we'll pick up here on Friday.